In this video, we discuss learning outcome number 4 from lesson 5.2, which is about computing the mean, variance, and standard deviation of a binomial probability distribution, and then using those along with the range rule of thumb to determine if a value is significantly high or significantly low. So here are the formulas. That first one's actually very intuitive. If you have n trials and the probability of success in one trial is p, you just multiply those together, and that's the expected value over an infinite number of trials. And remember, expected value and the mean are the same thing. So let's say there were 30 questions and there were true-false questions and you were guessing. The question is, well, what's the mean number of questions that you could expect to get correct if you had 30 true-false questions and you had a 50-50 shot of getting each of them correct? We just take 30 and multiply it by half. You'd expect to get half of them correct, and then you would get 15. That's the mean. So this is exactly what you would expect, and we don't have to compute the mean of this probability distribution in the same way that we calculated the mean in other sections. So we don't have to find all of the x values and multiply them by the probabilities and then add them together to get this mean. It turns out with binomial distributions, it's exactly what you'd expect. It's just that probability of success in one trial times the number of trials, and that's our expected outcome. To find the variance, all you have to do is take the number of trials and multiply by the probability of success and the probability of failure. And then if you take the square root of that, you'll get the standard deviation. Now, recall the range rule of thumb. We've talked about this many times. We say that if a value is within 2 standard deviations of the mean, we're going to say that those values are not significant. They're sort of typical. And any value that is more than 2 standard deviations above the mean, we're going to call significantly high. And any value that is more than 2 standard deviations below the mean, we're going to call significantly low. So if an x value is less than or equal to this value, it's a significantly low value. Or if an x value is greater than or equal to this value, it's significantly high. But graphically, you can see it right here. It's just an x value in the far right tail or an x value in the far left tail. The ones on the left are significantly low. The ones on the right are significantly high. And the insignificant values are the values that are sort of typical, lie within 2 standard deviations of the mean, according to the range rule of thumb. Now, this 2 standard deviations from the mean is not necessary, but it is what we use in our text and it's what we use in our course. Now let's apply this in a familiar problem. We are using parameters to determine significance here. It says standardized tests such as the SAT, ACT, and MCAT typically use multiple choice questions with 5 possible answers, one of which is correct. Assume that you guess on the first 4 questions. We've seen this problem before, something like it. This time we want to compute the mean and standard deviation. So that's the mean number of correct answers if you were to guess on 4 questions infinitely many times. And we also want to compute the standard deviation, which is a measure of that variation in your data set. And then once we have that mean and standard deviation, we want to use the range rule of thumb to determine if 3 correct guesses out of 4 guesses is significantly high. So first we'll calculate the mean. All you have to do to calculate the mean, oh wow, that's very large. Let me make that small again. All right. All we have to do to calculate the mean is multiply the probability of success in one trial by the number of trials. So you've got 4 trials, 4 questions. The probability of guessing correctly is 1 in 5 because there are 5 possible answers. So if you take those and you multiply them together, you get 0.8 as the mean. So after a really long time, if you were to do this over and over again and then look at the number of correct guesses out of those 4 trials and you were to repeat this whole thing, we would call that one trial, and then just keep doing that over and over and over again. If we were to calculate the mean of that for infinitely many trials, then we would get 0.8. So 4/5 of a correct guess on average over the long haul as you continue to choose 4 problems and guess on all 4 of them. To find the standard deviation, we just take n and we multiply by n, or we take n and we multiply by p, that's the probability of success in one trial, and then we multiply by q, that's the probability of failure in one trial, and you take the square root to get standard deviation. If you don't want the standard deviation, if you want the variance, just don't take the square root. So we've got 4, that's the number of questions that we're guessing on, times that 1/5, or 0.2, and times the failure probability. So if you have a 1 in 5 chance of guessing correctly, you have a 4 in 5 chance of guessing incorrectly. So you've got 4 times 0.2 times 0.8. Take the square root of all that, turns out to be 0.8 as well. That's just a coincidence. So you end up with 4/5 of a correct guess as your standard deviation. Now, if you're trying to make sense of these numbers, the mean is easy to make sense of, but the variance or the standard deviation is a little bit harder to make sense of. But remember what we said with that range rule of thumb, most values, typical values, tend to lie within 2 standard deviations from the mean. Now, that's a very rough rule of thumb, but it's the one that we use over and over again in our book and in our course. So in order to determine whether a particular number of correct guesses is significantly high or significantly low, we've got to find out what those bounds are for those typical values. So we need to compute the mean minus 2 standard deviations and the mean plus 2 standard deviations. Now, in this case, when you subtract 2 standard deviations from the mean, you get this negative value of correct guesses, which doesn't even make sense. But if we're just looking at the numbers, that lower bound is negative 0.8 of a correct guess, 1 or 8 in 10, or 4/5 of a correct guess, but negative, which doesn't quite make sense, but that's the value we get. If there was any number of correct guesses that was lower than that, then that would be significantly low, but there's not, because there are no numbers of correct guesses that are negative. Now on the high end, if we take that mean and we add 2 times the standard deviation, we get 2.4 correct guesses. So any more correct guesses than 2.4 is significant. Now we were asked to determine if 3 correct guesses out of 4 was significantly high. Since 3 is not in this range between negative 0.8 and 2.4, it's not typical. Any number of guesses beyond that interval is significant. Since 3 is greater than 2.4, that's the upper limit. An outcome of 3 correct guesses out of 4 guesses is a significantly high outcome. So that's how we can use that mean and standard deviation to determine whether a particular value is significantly high. If we were given a value and asked if it was significantly low, it would just need to be lower than 2, or the mean minus 2 standard deviations. And we're going to look at significance again in learning outcome number 5. I'll see you then.